Hi, I have a question.
Yes.
Um, I have two questions. One is that when we did the type 2 string theory, superstring, can you hear me?
Yeah. Yeah.
Yeah, we found that there is a RR sector
Yes.
in the vacuum state, and in the vacuum state there is a RR sector, and it leads to an interpretation that there are some D branes in the target space, certain kind of.
RR sector is not deviance in the target space. RR sector is just one more some state of the closed string.
What I wanted to ask was that in type 2 string theory, we have an argument to say there are certain D branes, and another way to describe D branes is that there are some open string. But when we do type 2 superstring, we start with these closed strings. And how do we end up having open strings in the
Yeah,
theory?
that we have not discussed yet. It's the same as in bosonic string theory, that you have to add D-branes as extra objects. If there are no D-branes, there are no open strings in the spectrum, right? So it depends on what background you put. So type 2 string theory, as I have discussed, right, with purely closed strings, that's a consistent background.
Okay.
Right? On top of that, you can put D-branes, and the D-branes carry both Raman charge and NS charge. Right? So it's not that they only carry RR charge, they carry tension also, right, which is a source of gravity. So that we'll discuss later. So far, we have not discussed D-branes at all in type 2 string theory.
All right. And I have another question. So far we found that there are three kinds of superstring. One is type 2A, B, and heterotic.
Yeah, two
For the
kinds
case.
of heterotic, in fact, yeah.
Yeah, two kind of heterotic. Are there similar classification for the open superstrings as well, or they are just?
Yeah, so there is a single consistent open superstring theory, that is a type 1 theory.
Okay.
Yeah, so which again I have not discussed so far, because that will
But you will discuss it later on?
That will be discussed when we discuss D-branes and orient defaults.
Okay, thank you.
Any other question? Okay, so let me remind you where we are. So last time we discussed heterotic string theories, and we said there are two possible heterotic string theory, and we discussed one of them in detail. Okay? And that is the SO32 heterotic. So today we are going to discuss the next other one. Okay? So let me remind you what the other one was. So the field configuration was X mu, then psi mu plus. Okay, these carry positive chirality. Okay. And then we had 32 left moving fermions. Okay. We are now going to divide this into two sets of 16 each. Okay. So let's call these eta A minus, A is not eta capital A minus, and chi B minus, okay, with AB running from 1 to 16. Okay. And on the worldsheet, we are going to identify this configuration with X mu minus psi mu plus eta A minus chi B minus. This is the usual identification on the right moving sector. Okay, this is the reason why I have to do a GSO projection, and you have to also consider Raman sector on the right moving sector. Okay. But we also identify this with X mu psi mu plus minus eta A minus chi B minus, and with X mu psi mu plus eta A minus and minus chi B minus. Okay. So the main difference, if we think compare with the historic to heterotic, okay, was that this identification was as before. Okay. And then there is one more identification where we change sign of both eta and chi. Right? So you could combine them into one single set of fermions, which you had called lambda. Okay. Here you are dividing into two sets. You can independently change the sign of eta A or change the sign of chi B. Okay. So there is altogether Z2 cube identification, right? Because the first Z2 changes the sign of this, second Z2 changes the sign of this, and the third Z2 changes the sign of this. So there will be 8 sectors, and there will be 3 separate GSO projections, right? One on the right sector, okay, the GSO projection that changes that says that all states have to be invariant under this transformation. Okay. And on the left sector, all states have to be invariant under this transformation as well as under this transformation. Okay, where you can change the sign of eta and the sign of chi.
Division only 8 and 8, not like I mean Z cube. I mean we could have Z to the power 5.
Yeah, so that is because of modular invariance. I said that there is only 2 ways we can construct modular invariant theories, and these are the 2 choices, right? One where you change the sign of all 32 fermions at one go, or you change the sign of 16 fermions and 16 fermions independently.
When we changed sign of both 32 fermions together, that was the
SO32.
But there were like 2 GSO projections there.
Yeah, because there is one on the right, psi to minus psi. No, on the right there is only one, psi mu to minus psi mu. On the left there are 2 independent GSO projections, right? Because you have to demand that it should be invariant under change of sign of eta as well as under change of sign of chi. Right? Whereas earlier you are demanding that it should be invariant under the simultaneous change of sign of eta and chi. Right? So that you can bunch them all into one set of fermions. Is this clear? There will be 3 GSO projection operators now. Right? 1 on the right and 2 on the left.
And 016 would have been like the 4th one is not there, the 3rd one is minus eta minus I.
Oh no, that will be SO32. SO32 minus eta minus. Yes, you are not discussing O16 times O16, that's a different theory altogether. Right? This theory that I have discussed, that I have described, looks like its symmetry is SO16 times SO16. Right? But we will see why it's called 8 cross 8. Okay, at this stage, the symmetry is SO16 times SO16. Is that clear? Okay. So we'll be constructing the spectrum of states. Okay. And for that, again, the states will be have the following form. So first of all, you have product over n mu, alpha mu, I'm not sure what I call this. Make it a name anyway. Mu r. And then we will now have to consider 2 sets of oscillators, one for eta, one for chi. Okay. So let's call them D and E. So product over R and A. Sorry, let me call it S. Okay. And now in the NS sector only it's leveled by the Fock vacuum K. Okay. If it happens to be the Ramond sector, okay, then it will carry spinor index. Okay. So let me write those. So A, this is the spinor of SO9, 1, and then there are two more spinor indices. I have to find some names for those. Okay, for now let's just call this alpha and beta. This is spinor of SO16, the first SO16, and this one is the spinor of second SO16. Okay. So these indices, whether these indices are there or not, depends on which sector you are considering. Okay. So for example, if we consider NS, 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 NS. Okay, the right goes on the right. Okay. This has no index, no spinor index. If it's R, NS, NS, then it has only A. Right? Because it carries spinor, sorry. I should have written other way. NS, NSR. Maybe I should have written the other way, right? Right should come on the right. Alpha, beta, A. Okay. So this goes here, spinor of SO9, 1, and then these ones go here. Okay, so left has these two indices, SO16, 1 and SO16, 2. The right has the index of SO9, 1. Okay. So NSNSR has only A. Okay. If we take R, NS, NS, this has only alpha, right? And NS, R, NS. This only has the index beta. Okay. And from this you can read out the other things. For example, RRR will have all three indices. Right? Because RRR will mean that it's a spinor index of SO16, 1, spinor index of SO16, 2, and spinor index of SO9, 1. Is this point clear? Right? Because the spinor index are coming because the zero modes, right, in the Ramond sector, okay, these indices are integers. Right? So let me remind you, right, that consider RNSNS sector. Then d mu minus r, okay, here r is half integer plus half. R belongs to z plus half. Sorry, d mu minus r. D tilde mu minus s. Here s belongs to z. Okay, because it's r left. And e tilde mu minus t, t will belong to z plus half. Right? Because this one, okay, has integer index. This is a Ramond sector. Okay, which means that there is zero mode, right? D mu 0. Okay. So we'll have the Clifford algebra. Sorry, D not mu. These are A and B. Then you have dA 0, d tilde 0, d tilde A prime 0 equal to delta A prime. Okay, so this is the Clifford algebra. Of SO16, right? Because A runs over 16 values. And then when you construct the ground state, it will be a spinor of SO16. Is clear or not clear? Right? Because you have to, so the way you do it is that you take the 16 fermions and make this into complex fermions, right? 8 complex fermions, right? So the way, so combined 16 real fermions to 8 complex fermions. Okay, so for example, we can take F1 0 as D1 D tilde 1 0 plus I D tilde 2 0. Then F1 0 the 1 equal to 2. Because F bar will have a 1 over root 2 D1 0 D tilde 1 0 minus I D tilde 2 0, right? So when you calculate the anti-commutator between F and F bar, you will get 1, FF will be 0. F1 0 is F1 0 is 0, and so is F bar 1 0 with F bar 1 0. And similarly, we can do for other things. F2 0, F bar 2 0 is 1, and so on. And similarly, we get F8 0, F bar 8 0 equal to 1. Okay, just combine the 16 real fermions into 8 complex fermions. Okay. Then start from a ground state, call this omega, okay, such that Fa 0, F, you have to find get another index. Fm 0 acting on this is equal to 0 for m equal to 1 to 8. Okay. And then the Hilbert space, the ground, okay, so the Hilbert space in 0 mode sector are given by F bar m 0 acting on 0. Right? You just apply F bar m 0 as many times as you like. Right? Fm 0 annihilates it, so you cannot, so none of the F8 0, none of the Fm 0s for m equal to 1 to 8 you can apply, because by definition the ground state is annihilated by those. Okay? But F bar m 0 you can apply as many times as you like. Right? As many times as you like meaning once. Right? You cannot apply more than once. Right? Okay? Because square of that is 0. Okay? So how many states are there? 2 to the power 8. Right? So this gives you 2 to the power 8 states. Okay? But then you have to worry, remember that you have GSO projection. Right? So if the ground state is, if omega is GSO invariant, right, then you can apply only even number of F0Ms. Right? Because F0M is changes sign under GSO parity. Right? So you can only apply even number of F0Ms. Right? So this cuts down the total number from 2 to the 8 to 2 to the 7. Is clear? 2 to the 8 over 2, right? So after GSO, so this gives you 2 to the 8 states. 2 to the 8 states. After GSO, we get 2 to the 7 states. Okay. So on the left, the Ramon sector ground state of SO16 1 is 128-fold degenerate, right? 2 to the 7-fold degenerate.
We could also cut it down by half by taking only while spinners kind of thing.
No, we have already taken while spinners.
No, but then we should have started with what you said. So you're saying you started with
Okay, you are asking whether it's a complex or not, right? So that we have not discussed. Yeah. So Maradona or whether it's real or complex, we have not discussed, right? That you can check whether it's real or complex, right? Whether it's a complex representation or a real representation. Yeah. So you have to complex conjugate it and see if it is in the same sector or outside the sector, right? And in this case, it's a real representation. If you take complex conjugate, that also satisfies the same condition.
Is it a different representation?
No, it's the same representation.
Actually,
2 to the 7 real states. 2 to the 7 real states.
we was counting for the SO32.
No, SO16.
No, now we are doing SO16. But in the SO32 heterotic theory,
Yeah.
instead of having these two levels, I mean,
So you got 2 to the 15, right?
so we started with 32 SO32 spinner level, which is 16. No, it is 32 real for me.
2 to the 32. 2 to the 16.
Yeah,
2 to the 16. Then we cut down by half, right? Again, because of the GSO projection.
We start, so SO32 spinner representation should be in principle 2 to the 16 complex dimension.
That is only if you before you demand while condition.
Exactly. Now you
Yeah.
can demand while or my
Yeah. See, real or complex, right? That depends on whether when you complex conjugate, whether it provides a different representation or not, right? That we are not studying here, right? You can do it.
No, that's a choice we have to make.
No, you don't have that choice.
We think from the target space.
Hmm.
Like SO32 is a gauge group, and I want to couple the physics to some fermions. No, okay, space time, whatever, but I want it to couple to some spinorial object of SO32.
Yeah.
Now I can choose that spinorial object to be either while or complex or Dirac.
No, but we are constructing the states explicitly here, right? See, suppose you complex conjugate. Let's see this. Suppose you complex conjugate everything, right? Okay. So then what's going to happen? The F01 will become F0 bar 1, right? Under complex conjugation. Okay. Omega, what will happen to omega? Omega will now go to a state that is annihilated by all the F bars, right? So which basically means the omega will go to a state which is all the F bars acting on omega, right? Okay. Now you construct the set of states, right? And you see whether the original set of states that you have constructed, right? Say F bar 1, F bar 2 acting on omega, right? You take its complex conjugate. Is it already part of representation or not? Right? Well, how do you know it was in this case? Omega, yeah, omega becomes all the F bars acting on omega, all the F bars acting on omega. Now you are applying F1, F2, right? And that's part of the same representation because it's even number.
By this, we conclude that this 2 to the power 7 states from a real
Yeah.
Of SO30.
Of SO16.
SO16. So that should be held in the target space as well, this state.
The target space states we are constructing from the worldsheet, right? So from the worldsheet, we are seeing that we include this precisely 2 to the 16, 2 to the 15 states. Sorry, 2 to the 7 states in this case.
Yeah.
In target space also you have 2 to the 7 states because target space states are constructed from the worldsheet. Right? It's like you construct a graviton state, right? You didn't have a choice that make graviton into a complex field. Right? So whatever worldsheet gives, you have to accept. Right? Yeah. No, so the point is, if the worldsheet tells you that you have to add complex conjugate, you add it. If it doesn't, you don't add it. Right? Because the worldsheet is determining the spectrum.
16 real fermions, you mean this D tilde A 0 dagger is D tilde A 0?
Yes.
And that we have
That's
to,
right. That is part of the worldsheet prescription. You guys Majorana file, right? That you have specified. In the worldsheet, it's Majorana file. Okay? Otherwise, the central charges will not match. Okay? I mean if you make it complex, right? Central charge will double, right? BRST operator will not be nilpotent, right? Many things will fail. Just like X mu's, you couldn't have declared them to be complex fields, right? Okay, so the psi mu pluses we have declared that it's Majorana file, right? And we are working with that.
Construct this 8 complex fermions.
Yeah.
Then construct the ground state and see that it is 2 to the 8 degenerate. There are 2 to the 8 states, but after GSO projection, only 2 to the power 7 will remain.
Yeah.
Which is 128.
Exactly.
And then 120 plus 128.
Yeah, we'll see where it comes from. So Raman sector is 128, right? That's what we see. Raman sector ground state. Okay, what significance it will have, we'll see later, right? At this stage, you only know the Raman sector ground state is 128, and similarly for 16.2, the same construction will work. The Raman sector ground state will be 128 dimension. Other sector. Okay. So these indices, right? This alpha, beta, A. Okay, this alpha and beta each run over 128 values. Okay, because these are the Raman sector scalar indices. Yeah, K0 should be omega. Where did I say 0? Oh, yeah.
About why we call this T is Majorana fermion. Like T square is not 0. You say it before.
Yeah, but that's just the fact that two real numbers commute, right? But two real operators don't commute. Right? So these are, what we have done is that we have taken the conjugate momentum, right? And when we impose the commutation relation, right, we replace the commutator by anti-commutator. Right? That's the sense in which they are fermions.
Condensed matter literature, they don't call it fermions. They just call it Majorana modes and they combine them to construct the fermions.
No, I think they call it fermion. There is a difference between Dirac fermion and Majorana fermion.
Yeah. What is the usually we define oscillators using F and F bar,
not using this D.
Right? I mean,
F and F bar.
F square is 0.
Yeah,
F square is 0, yes. Yeah, exactly. Yeah. And those are Grassmann odd now variables, right? So they are fermions in that sense.
Like these can be like combined to get fermions.
No, these themselves are fermions, right? Majorana file fermion. See the way we quantize, right? We took the conjugate momenta, okay, and then impose that the Poisson brackets become anti-commutators, right? That's the signal that we are dealing with Grassmann odd variables, right? That's a signal that these are worldsheet fermions.
Always that in this case the conjugate momenta is that operator itself.
True, yeah.
It's more convenient to go in the FF bar basis.
Yeah, if you use the FF bar basis, then that problem is not there, right? Then the conjugate momentum is F bar. And then you impose that FF anti-commutator is 0, not FF commutator is 0. Similarly, F bar anti-commutator is 0. And FF bar anti-commutator is 1. Yeah.
Like if we exchange like two particles, then like this ds doesn't go to minus of like what happens in fermions.
See, this issue is independent of whether it is boson or fermion, right? The fact that if you use the real basis, it's a constant system, right? So you have to do constant quantization. Even for the bosonic objects, you have to do that, right? If there's a constant system, you have to use constant quantization, right? That's independent of whether it's Majorana or Y, right? Dirac bracket has to be replaced by commutators when they are bosonic, and they have to be replaced by anti-commutators when they are fermionic, right? The fact that it's a constant system means you have to constant the Dirac bracket. Right? That is true in whether it's bosonic or fermionic. Right? So this FF, this form, right? This is coming from Dirac bracket. Not this form, this form. Right? This is coming from the Dirac bracket. right? And we have replaced the Dirac bracket by anti-commutator to get this. Is this clear? So let me write down the L0 and L0 bar constant, L0 tilde constant. So from this, we see that we have L0 will give you sum over n
equal to 0. That's one.
we
Plus C on the left
oh
side.
oh okay plus c equal to 0. And now the results again from unitary analysis, but you can also get it from BRST, right, which we'll discuss later, is that C is minus half in NS and 0 in R. Okay, this is on the left, on the right. Okay, because this is the right sector, right? L0. C tilde is minus 1 in NS. This is 0 in NSR and RNS, and it's 1 in RR. Oh, I should have put this alpha prime k square by. Okay. So to compare with what we got last time, right, this is the same, right? Right sector hasn't changed at all. It's the same as superstring also, right? NS minus half, Ramon 0. On the left sector, NS is like a bosonic string. C tilde is minus 1. Okay, in the bosonic string case, also you had C tilde equal to minus 1. This was also true in the exothermic heterotic case. In the NS sector, it was minus 1. Okay. RR is like you are putting periodic boundary condition on all the formulas, right? This should coincide with the periodic boundary condition in the SO32 sector, R sector of SO32, and that was indeed C tilde equal to 1. This is extra, right? Because these sectors are not there in the SO32 heterotic case, right? You either put anti-periodic on all the fermions or periodic in all the fermions. This is a new result, this is 0, right? But perhaps it's not so surprising that this is 0, right? Because this is somewhere in between this and this, right? Here it was NS. No, it's not. I mean, it's a. If you think that the shift is coming because of the twisting, right? Here you went from here to here by twisting 32 of the fermions, right? That changed from -1 to 1. Okay? If you twist only 16 of the fermions, you expect it to be half of that. Okay? So the shift should be 1, and that gives you -1 plus 1, which is 0.
Should be algebraic addition of all this directions.
Exactly. Because you are calculating the ground state energy, essentially, right? We have to do some zeta function regularization of the ground state energy, right? Normal ordering constant basically comes from ground state energy. Right? If you use the zeta function regularization, you can get all this. Is this clear? Okay. So with this, we can now try to construct the massless spectrum. And we'll do it separately in the left and right. Massless sector. So basically, this means you have to set k square equal to c, right? If you're looking for massless sector. Yeah, we'll see that. Okay, there are no tachyons. Yeah, that proof is the same as earlier because on the right, there are no tachyons. Yeah, so k square, just from analysis of the right sector, right, physical states, you know that k square has to be positive, right? Yeah, k square is the same on both our left and right? So once you have shown that on the right k square is positive or 0, then you have shown that there are no tachyons. Is this clear? Right? Because you have to do this k square satisfy both conditions on the left and right. Right? Both conditions have to be satisfied. So as long as one sector you can show that there are no tachyons, it's true in general. So what are the massless sectors? Let's look at NS. So on the right, first we look at the on the right. Then finally the full spectrum will be constructed by taking the product of left and right. Okay. So on the right, let's look at the NS sector, right? What are the massless sectors on the NS side? These you have constructed many times by now.
Only one loss.
Pardon? Yeah. On the ground state, you have to apply one oscillator, B oscillator, right? So B tilde mu minus half. B mu minus half. Okay, because this minus half is going to cancel this C equal to minus half, right? And give you this combination will make it 0. And you have to this has to satisfy. Let me put a zeta mu, and you have to satisfy this k mu zeta mu equal to 0, right? Okay, this I can impose at the end after combining the both left and right. Okay, right now let's do the L0 only. Okay, in the Ramon, what are the massless sectors? It has come from the Ramon ground state, right? When Ramon sector, you see C is 0. You cannot apply any oscillator, right? It just comes from the ground state. So it's basically Ka. Provided on the right, on the left you find. Because you have to, the final spectrum is a product of massless sector from the right and massless sector from the left. Right? Where the Hilbert space you are constructing by product. So as long as, so for every one of these, right, any massless sector that you find on the right, you take the product and that will be a massless sector, massless state. Okay, if the right sector doesn't have a massless state, then of course you will not get, right? Because the same k square has to satisfy both conditions. It does have, yeah. basically the supergravity sector. On the left. NS. What states can we get? Alpha. Okay. Alpha tilde mu -1 acting on K. 2. Yeah. So D tilde and so give me a state. D tilde A. D tilde, sorry, this we call it A prime. D tilde A, D tilde B minus half. D tilde B prime minus half. Then D tilde. So those are all there. You have forgotten something. So what are the conditions that the state has to satisfy? GSO projection, right? And D tilde and E tilde are or under GSO, right? There are two GSOs, right? One changes the sign of D tilde, the other one changes the sign of E tilde, right? So you can only put two D tilde, two E tilde, right? Not the cross, right? This was not the case in SO32. SO32 GSO was simultaneously changing the signs of D and E, right? That's why we call it one oscillator, right? There you could put this A could be any of the 32, right? Is clear? So how many states are there? This is of course 10, right? And you have to put the appropriate projection condition, the K mu condition that will do later. The L1 condition, right? The analog of the K mu zeta mu equal to 0, right? Yeah, K dot zeta equal to 0. Yeah, that has to be put at the end, right? But otherwise it's 10. But let's look at these. How many are there of this type? A runs from
128 square.
it's antisymmetric, right?
Okay. 128 times 127 by 2.
Adjoint of SO16. Because this is 16 times 15 by 2, right? That's 120, right? So 120 states adjoint of 120 states adjoint of SO16 of SO16-1. And this gives you 120 states adjoint of SO16-2. Is clear? So when you take the product of this with this, that gives the graviton-dilaton antisymmetric tensor, right? The mu index. Okay, let me call this nu. And when you take the product of this with this, you will get the space-time gravity, right? Because there's a spinor index and a vector index. Okay, that gives the space-time gravity. What about this product? That will give you the SO16 adjoint gauge fields, right? The vector fields with a mu index. And similarly, this will give you SO16-2 adjoint fields, right? Vector fields. Okay. And these will give the supersymmetric partners of those. Okay, spin half or not spin half, it carries spinor index. Spinor of SO9, 1. And adjoint of SO16. Is this clear? Why this 120? Because it's antisymmetric in A and A prime, right? These are fermionic oscillators, right? So you get 16 times 15 by 2. Right? That's 120, and that is the adjoint of SO16. This is just group theory. If you take the product of two fundamentals of SO16 and take the antisymmetric part, right? That is the adjoint representation of SO16. Okay, let's look at RNS. In the RNS, C tilde is 0. Right? So you cannot apply any oscillator if you are massless state. Okay. So then the only possibility is A alpha, that alpha index, right? D tilde 0. And no oscillators acting on it, right? So this gives you, we have already seen 128 states. P naught of SO16, 1. Okay, we'll come back to the interpretation of this later. NSR, let's do this. This K beta. This is again 128 states. P naught of SO16 2. Is this clear? What about RR? C tilde is 1. So nothing will work, right? You cannot get massless state in RR. Okay, so this is my, from RR it's empty. Pardon? Yeah, this was true in previous case also. Right? RR sectors, there it was, we are called R sector. Right? There is only one subprojection. So these are the massless states. Okay. So you have a product of this and this. Okay. Right? This is a space-time vector. Right? Carries spinor index of that gauge field. Right?
If it's massless, shouldn't it also be a...
Yeah, so that only there the only alternative is it has to be a gauge field. Right? It's a gauge field in the spinor representation of SO16 gauge field. See, if it's a massless vector, right, then you cannot have a consistent theory unless it's a gauge field. Okay, so for that tells us that it is a gauge field, and it transforms in the spinor representation of SO16, which is also a gauge group, right? Whose gauge field you have already found. Right? Is this clear? That's what you have found is a set of massless vectors, right, which transform in the spinor representation of the SO16 one gauge, right? And another set of massless vectors which transform in the spinor representation of SO16 two gauge group. So how can you make it into a consistent theory? Imagine that you are in SU2 gauge field, just for 3 plus 1 dimension, SU2 gauge field, right? And you found some other massless vector fields which are transforming the spinor representation of the SU2 gauge field. Can you write a Lagrangian, consistent Lagrangian of that describes this theory? We know how to couple fermions in spinor representation, scalars in spinor representation to gauge fields, but not vectors in spinor representation. Yeah, so gauge field will already come with its adjoint field. That you have already got, right? Okay, now you are saying that there are some extra spinors, right, which transform in the spinor, extra states which transform in the spinor representation of the gauge field.
So you expand the gauge group and say this is the
Yeah.
point of that gauge
So the only alternative is that if you can find a different gauge group, right? Say that the actual gauge group is bigger than SO16, right? Whose other missing gauge fields are these? Yeah, that is a vector, yes. That we have already found 128 state, 120. Spinor representation of SO6, right?
Then it should be adjoint to some bigger.
So it has to be adjoint of some bigger group, right? So the only way the theory can be consistent if the whole thing becomes an adjoint of a bigger group.
So we know that we have to add the 128 generators. 120. So we know the count at least.
Yeah. So you have to find out what is there a gauge group? Is there a group, right? Which contains SO16 as a subgroup, right? And whose adjoint is a direct sum of the adjoint of SO16 and the spinor representative of SO16.
We might be lucky to find one.
Yeah, if you are not lucky, then theory cannot be consistent, right? I mean, there is no low energy description of this system, of this theory. No, that two SO16s you already have from here, right? Now you have got some extra states, right? Vector states. This is transformation is spinor representation of SO16, right? Now let's imagine that it's some other, let's suppose it's U1 to the 120. Why not, right? You have found 128 extra gauge fields. Let's say it transforms into U1, there are 128 U1s. Okay? The problem is that if it's 128 U1s, right, it cannot be charged under another gauge group. Right? Then the gauge group you are declaring is a product. It's SO16 times U1 to the 128, right? But then those gauge fields cannot transform in the spinor representation of SO16. Right?
It has to have a non-trivial commutator in that.
Exactly. So it has to have a non-trivial commutator. Right? So the gauge generators don't commute.
Classification of this Lie algebra will help us to find.
Exactly. So you look at the classification of a Lie algebra, and the only group that does this is E8. Right? Yes, E8 has an adjoint representation which is 248 dimensional. Right? And E8 has an SO16 subgroup under which the adjoint splits into 120 plus 128.
Bigger group.
No, because where are the gauge fields? Right?
We have not found.
We have not found any gauge field, right? It couldn't be a bigger group. Yeah, it couldn't be a bigger group.
Product structure, like adjoint and
But it cannot, if it's product, it will be adjoint of the first group times adjoint of the second group. Right? Suppose the group is G1 times G2. Then the gauge fields will transform in the adjoint of G1, singlet of G2, and singlet of G1, adjoint of G2. It couldn't have transformed as spinor of G1, right? So G1 has to be expanded. So the new group that you are looking for has to contain G1, and it cannot be a simple product. It can be any subgroup as long as it fits.
Actually get I mean, the exceptional group is to actually check all the things, right? I mean, how do we, practically, let's say this is the problem.
Yeah. So of course you have to check that all the interactions are invariant under E8. Right? At the level of the spectrum, we are saying that the E8 is the only possibility. Okay. Then you have to worry about whether the interactions are invariant under this E8, right? Whether the theory is consistent. But even without going into interactions, what we see at this stage, that just at the level of the spectrum, right, the only way that you can fit this into a consistent theory is to declare that the gauge group is E8. Adjoint of E8. And the fact that they actually fit into adjoint of E8 is a group theory statement. Right? That the adjoint of E8 splits into 120 of SO16 and 128 of SO16. Right? If it didn't happen, you couldn't do this.
Vector fields.
Yes.
Vector fields transforming in these spinner representation
of SO16.
Is there a simple example, like a low level example? SU2 level.
Yeah.
Where like we have, I don't know, maybe.
Yeah. Imagine that we had SU2. Let's suppose we had SU2, right? And we had found that there are some vector fields in the spinor representation of SU2. Okay. Could you, is this a consistent theory?
Yeah, I agree with that. I agree with that.
No, you agree with what? Is it consistent or not consistent? Which statement do you agree with? SU2?
I cannot.
You cannot do that, right? But suppose that we learn that there are two spinor representations and one singlet of SU2, all vector fields. Then you could put this into adjoint of SU3.
Oh.
Right? The adjoint of SU3 will split into adjoint of SU2, a spinor of two spinors of SU2, right? From these two off-diagonal ones, and then a scalar. Right? So that will give you 3 plus 4 plus 1. 8. Those are the 8 generators of SU3. Right? So it's a non-trivial statement that the extra states, vector states that you are finding, right, actually fits into a group that contains SU2. In the adjoint representation of a group that contains SU2. Right? So that's the example. That if you had found that you have a theory, right, for some reason, suppose you didn't know Lagrangian or anything, right, just by doing some low energy analysis, you are looking for a spectrum, you find that there is an SU2 group, and you have a vector field of SU2 and two vector fields in the adjoint of SU2, two vector fields in the spinor of SU2, and one vector field in the singlet of SU2. Right? Then you know that the group has to be SU3.
Do we have to check this? I mean, let's say this is on free theory level stuff, but and we figure out some group, let's say SU3 for the simple case.
Yes.
And then we started adding interactions, which is consistent with SU3.
Yes.
So we have to check that every order perturbative.
Yeah, so all orders, you have to make sure that it's consistent with SU3. Yeah, so here you have to check to all orders that it's consistent with the 8. Because the theory that way you have formulated is not manifestly 8 symmetric. Right? So I'll describe a way to construct it which makes this 8 more manifest, but it's also more complicated, right? It's more unfamiliar territory. Fermions are easier, right? Even though the full symmetry is not manifest, at least one can understand what it is, right? All the rules are clear. No, not irreducible. Irreducible is fine. But it has to see the point is ultimately it has to be adjoint. Vectors have to be transformed in the adjoint of the gauge. Right? So U1 to the 16, you can take products of U1s. So then the representation adjoint is one dimensional, right? So you can take a reducible representation, right? Adjoint of the first U1 plus adjoint of the second U1. But that doesn't fit. Because then it will not be transforming in the representation of SU16. Right? Because whatever group the adjoint, the gauge fields always transform in the adjoint of the group. Right? That is a general rule. So whatever group you propose, you have to make sure that these statements, right, whatever you have found so far, okay, is consistent with that proposal. Okay? And here it will not fit with any other proposal, okay, other than saying that it's E8. Is this clear?
Reveal that all the interactions also decouple in left and right.
No, interactions will not decouple because the K connects, right? In the zero momentum sector, yes, indeed, the interactions factorize, right? Otherwise, it will not, because if you look at the in the bosonic string theory, right, on the calculated correlation function, there is an integral d to z, right, and then there is a mod z1 minus z2 to the k square, right? So that integral doesn't decouple factor into left and right.
Yeah, I've actually meant that the interactions decouple in the etas and i's. Because we are writing everything as E8 cross 8, right? Not some bigger group.
which contains
Cross commutator.
You cannot fit into a bigger group. Then where are the fields then? Where are the gauge fields? If it is a bigger group, right? Suppose it's E16 or something, not E16, or whatever it is, not E16, some big SO group, right? Which contains, yeah. So you have to find the adjoint of that gauge group, right? That will have many more massless vector fields than what we have found.
You can either find a group or it has to be unique because of number of generators.
Yeah, typically, if you either find a group, if you don't find it, it's not a consistent theory. It could have been. First, let's look at the spectrum. Even at the spectrum level, it could have been inconsistent, right? It might not have fitted into a group.
Yeah, that's true. But
Right?
I'm saying after you started at 2 SO16.
Yes.
Because you had two independent etas and chi's. And each of them now you're saying, okay, they might really in targets is fix into E8 cross E8.
Yes.
The reason you're writing it as E8 cross E8 is because there's some decoupling of the two sets of
gauge group is really product, E8 times E8.
Yeah, so these E8 gauge field, E8 1 cross E8 2, and the 1 and 2 fields don't talk to each other.
At low energy level, no. Because if you write down the action for a gauge,
there's no commutator.
Yeah, exactly. If there is a commutator, right? Not at the low energy level. Through gravity interacts with everything, for example, right? Yeah. In a low energy, there is no interaction. You cannot write an interaction because you have two different gauge groups, right? Try to write a Lagrangian, which has SU3 times SU2, right? How can you introduce interaction between the SU3 gauge fields and SU2 gauge fields, right? At the level of the Lagrangian. You can do it through loops. There may be quarks which carry both SU2 and SU3 quantum numbers. Then through loops, you'll have some interaction. Yeah.
Is it possible that by constructing a spectrum, we find that the free theory is not possible? I mean, because we might not be able to find a group accordingly. But is it still allow for a interacting theory which can't be written down as a free theory at all?
See, because you are constructing this in perturbation theory, right? So the underlying assumption is that it is possible to do it perturbatively, right? Otherwise, you couldn't have done it the way we are doing it.
But for example, if we got stuck at this point that we can't write a free theory, then the other possibility is allowed, right? Although we are not doing it at that level.
Yeah, then we will declare that this way of constructing string theory is inconsistent. Yeah, you don't get a consistent theory, right? There will be another way to get this construct a theory, but not this way.
Trivial to see that we can't have vectors in spinor. Like we can't write a Lagrangian for that.
That for vectors in the spinor representation? Massless vector. Yeah. I think it's one can, if you try to do that, right, you lose gauge invariance, various other things, right? Because you have to have some gauge. I mean, in order for a vector field to make sense, right? For the extra ones, also you have to have a gauge invariance, right? Because the longitudinal modes have to decouple. Otherwise, you'll get negative norm states, right? So where will those gauge fields come from? Right? So it has to be gauge field, right? The massless vectors. No, there are many other groups. SO16 times U1 to the 128, right? That has 248 generators, right? Is that they are those generators will be all singlets under SO48, SO16, right?
But
so
the product has to be.
Yeah. So the point is that you are looking for a group, right, such that its adjoint splits into 120 plus 128, right? As far as SO16 is concerned, when you embed SO16 in that group, it should be 120 plus 128, right? That's the way the adjoint should split, right? If you take SO16 times U1 to the 128, right, then those would have been allowed, right? If these states, these 128 states that we are finding, had been singlets of SO16, right? Then in fact E8 will not be allowed, right? Then that's the only possibility, that those will be decoupled gauge fields.
Why does it always have to be adjoint representation?
Gauge fields are always in the adjoint representation. And once you have a gauge group, right, the gauge fields are in the adjoint representation of the gauge. Right? That's how we write the Lagrangian, right?
They can't violate this.
No, with the basic principle of when you write on a gauge theory action, just quantum field theory. This is not a string theory, right? Just in quantum field theory, if you try to write a action for a gauge field, the gauge field is always transformed in the adjoint representation. Yeah, you will not have gauge invariance, right? Because the cubic coupling of the gauge fields that is needed has an FABC, right? So ABC are adjoint representation. Right? So the gauge, once you have a gauge theory, the vector fields are always in the adjoint representation, right? That's basically, that's the only way you can construct a gauge theory. And then maybe other representations, right, which you add, right? But typically scalars and fermions you can add that.
We may even add massive vectors.
We can add massive vectors in principle, yeah. But not massless vectors, yeah. Like W plus minus, right?
Base group is bigger.
Yeah, W plus minus is charge under E1, right? So clearly you can have massive vector fields which couple to E1 gauge fields, right? But you couldn't make W plus minus massless, right? Then it has to be embedded in some SO3.
Is it to say that
Hi.
I write down gauge fields in apart from any other representation, I mean apart from adjoint representation, then I can't find a covariant derivative also which transforms it.
Exactly, yeah. Yeah, you can write a covariant derivative, yeah, exactly. Yeah. Sorry, was there a question?
Yeah. So can I say this E8, the gauge group E8 is broken into this adjoint of SO16 and the spinner of SO16, this
No, it is
120
not
plus.
broken because they are massless, right? So E8 is actually a full symmetry. It's not manifest. It's just that in this formalism, E8 is not manifest, but it's not broken because if it has broken, then these would have been massive states. Right? These 128 states. That's not the case here.
So the 120 state, do they transform under this 128?
Yes, they do. They do.
Okay, okay.
They have to. From what you have done so far, you don't see that, right? Because the E8 symmetry is not manifest. Right? But once you have said that these 120 and 128 states together form the generator of E8, right? Then the algebra of E8 determines how these 120s transform under 128.
Okay, thanks.
Generators and these generators will not commute.
From the fact that these are spinners of SO16.
Yeah, that's true.
All commutators are fixed, right?
All commutators are fixed.
Like just whatever is on.
No, 128 to 128 is not fixed. This with this is fixed.
Yeah.
But this with this is not fixed.
The constants are of SO16.
128 is a spinner of SO16, right?
Yes.
So what is structure constant there? No. Structure constant of SO16 will contain the commutator of 120s, right?
Yes.
So how a generator for 128 commutes with another generator of 128, okay? That information will come from E8 algebra. Right?
But I can still show, once I know the ES, I know the adjoint representation of that, I can show that it will split into.
Yes. Yeah, 128 plus 128.
But what would it mean? I understand, okay, like adjoint of SO16, I understand. What will the spinner, like splitting of algebra, what will that look like?
What will what look like?
Like, how would I know exactly that?
The group theory will tell you. See, the group theory tells you how the algebra of E8, how the whole set of generators of E8, right, split into the generator of SO16,
Okay, 120 generators transform
adjoint, and then 128 generator, yeah,
120 generators will transform under.
and under SO16, but in the spinner representation. Is this clear? So this is basically the spectrum, right? So what happens is that this SO32 and E8 cross E8 have very similar structure, right? Except for the gauge group, right? Both have supersymmetry that comes from the right sector, but and both have gravity, the gravity sector, right? The usual graviton-dilaton antisymmetric tensor and then the gravity nose. Okay? The difference is that in the case of SO32 heterotic, you have adjoint of SO32, okay, vector fields, and adjoint of SO32 spinor fields. Those are the gauge nodes. In the case of E8 cross E8, you have adjoint of E8 cross E8 vector fields and adjoint of E8 cross E8 spinor fields. Right? Only the group gets replaced. Otherwise, the structure remains the same. Adjoint of? Yeah. Adjoint of E8 cross E8 vector fields, yes. And the spinors, because you can take the product of any of these with these, right? Those will give the spinors. Okay, so let me just briefly say the bosonic formulation, although as I said, it's more complicated. So the idea is that these fermions have central charge half. Okay, bosons have central charge 1. So in some sense, a pair of fermions is equivalent to one boson, right? As far as the central charge is concerned. So the 32 fermions one might imagine that we can replace it by 16 bosons. Okay, this is what is called the bosonization. In 2 dimensions, fermions can be bosonized. Two, 1 plus 1, what is here? Now the problem here is that these were chiral fermions, right? So in some sense, these have to be chiral bosons. But chiral bosons are problematic, right? Because chiral boson means what? That it has only left moving degrees of freedom, no right moving degrees of freedom. Okay? But we have seen that for bosonic, the normal bosonic fields like x mu, right? The momentum couples left and right, the zero mode, right? So it's not the usual bosons, right? You have to make, so this is a CFT, but you have to construct this CFT by using some appropriate postulate, right? As an abstract CFT, not as writing down the action. Okay, you cannot write down an action and start quantizing to get this theory. Okay, because once you start writing an action, okay, when you quantize, it will the zero mode will couple left and right, right? If there is a momentum in the left, there will be a momentum on the right, and vice versa. So I'm going to tell you how to represent this in the bosonic description, right? Heterotic theory. Okay, we are going to replace the 32 fermions by 16 bosons. Okay? The lambdas. These are the lambdas. Or psi and chi. Right? This is in eta. Yeah, eta. Thank you. Eta and chi. By 16 bosons. Okay. But these have to be chiral. Okay. So let me first tell you the easy part of this. Okay. The easy part of this is when I mean by chiral boson, okay, that the oscillator part, okay, is like ordinary bosons. Okay. So 16 bosons, let me call this Y, I have to find another label, Ym. Okay, M runs from 1 to 16. It will have the oscillators. Which I can denote by beta m minus n. N belongs to integer. Okay, no GS of projection, no twisting, the normal bosonic oscillator. Okay? Tilde, yes, thank you. Okay. So we'll have the states beta tilde m minus n to the power okay, this what it acts on, of course, all the other oscillators are there. Fermions are not. The left moving fermions are not there. There is the usual K. The question is what I put here. Okay, about the momentum. So bosons are supposed to carry momentum. Okay. And this time we can put the momentum only in the left sector, not in the right sector. Right? So whatever momentum you write, it will not contribute to L0. Right? L0 contribution will remain as alpha from k square by 4. But here it will add. Okay? So let me call this some k. This is a 16-dimensional vector. Capital K. What should I call? Kappa. Okay, kappa. Yeah. Capital. Okay, P. Okay, fine. P. 16-dimensional vectors, right?
This is zero mode of ym.
This is zero mode of ym. Yes, indeed. This is zero mode momentum of ym. And now we basically specify what the allowed values of P are. Okay, what possible values of P can take. Okay. This comes again by demanding modular invariance, right? I'll not tell you how it comes, right? I have to specify what this P is. Okay. So modular invariance just like modular invariance fixed what kind of boundary condition you can put on the lambda I. Right? It tells you that the allowed values of P are either in E8 cross E8 root lattice or in 32 mod Z2 root lattice. Root lattice is something familiar to you? No? Yeah, SU3 root lattice tells you what are the representations that are allowed, right? That root lattice, yeah. Right? So E8 root lattice basically tells you what kind of E8 representations you are allowed, right? Okay. This is spin 32 mod Z2, right? Which is a little different from SO32. Okay. SO32 root lattice will contain the adjoint representation, the vector representation, the adjoint representation and whatever you get from the products. Okay. Like SO3 root lattice is different from SO2 root lattice. Let's look at the weight lattice, right? SO3 weight lattice and SO2 weight lattice are different. Is that clear why? Weight lattice means all representations are contained, right? Yeah, there is no spinor in SO3, right? So some elements of the SO2 root lattice will be missing from the SO3 root lattice. Okay? So when I say this is spin 32 mod Z2 root lattice, right? What does it mean? that this contains the SO32 adjoint. Okay, it doesn't contain SO32 vector. You can check if you look at the spectrum that we have constructed, right? SO32 vector never appears because starting from the NS sector ground state, we have to apply even number of oscillators, right? So even number of oscillators already tells you there is a projection, right? Vector representation cannot appear. Even in the massive sector, the number of oscillators is always even, right? Number of this detailed oscillators is always even, right? That rules are vector, but some spinor representations are allowed. Okay, so this is basically that whatever representations are allowed by this lambda, right? There is an invariant group theoretic way of specifying it, okay? And that's it. This root lattice. Yes, exactly. These are spinor adjoint products of SO32. E8 root lattice and weight lattice are the same.
There's no such thing as a vector of E8.
No.
There's no fundamental.
Yeah, there's no such thing as fundamental of E8. Right? E8 has all representations are there as part of it. Okay? So basically, this tells us what kind of P's are allowed. Okay? Those P's you put in that formula, right? So this will now get an additional term L0 tilde will get additional term alpha prime P square by 4. Okay, where P is constant to be this. And this generates the same spectrum. Whatever you got from the fermionic theory, right? Not just at the massless level, you can check, you can show that to all masses, massive order, it generates the same spectrum. Okay, so the way you construct the spectrum is that you pick any arbitrary vector P from this lattice, right? Either in the 8 cross 8 or in SO32, depending on which theory you are considering. Okay? Pick an arbitrary vector P and apply arbitrary number of these beta tilde oscillators.
Choice of R, NS, NSR and all.
Those are not, those are all gone. In the bosonic version, you don't have to include those different sectors. Everything comes from here. Exactly, yeah. Okay. The fact that you are allowing, for example, here, that the spin 32 mod Z2, which means adjoint of SO32 and some spinor, okay, that already contains that information, that those all these different sectors in the fermionic theory are there, okay, that you don't have to worry anymore. Which is infinite? Yeah, the infinite, yeah. But P square becomes larger and larger. So the infinite number of vectors, indeed.
If you are not restricted to the same massless things, then there should be a minimum number of choices. So
Yeah. Then if you are only looking at massless states, right? Then basically this choice is restricted. What you can choose here. Exactly, you recover exactly the same spectrum, right? That alpha prime P square by 4, right? This alpha prime P square by 4. Here we got these from these oscillators, right? In the massless sector, we got this 1, right? We got by applying these, right? This has minimum value 1. So the massless sector basically comes from when take alpha prime P square by 4 equal to 1. Right? That one cancels that -1 that came from the C tilde. You remember the C tilde was -1, right? Now all these sectors are not there, right? This C tilde is just -1. Okay? And that has to be cancelled by choosing appropriate P. Right? And the P's which satisfy this are the adjoint of E8 times C8 or adjoint of SO32 heterotic.
Does the C,
Hmm.
they are just fixed.
Exactly. Yeah, because there are no different sectors. C tilde is -1. C is the same. C is 0, no, minus half in the NS sector and 0 in the Raman sector. C we are not changing at all, right? C is on the right side. Yeah. So C, there's no change at all, right? The right side is unchanged. C tilde information? C tilde is just -1. It's as if it's all NS, right? Because these sectors are not there. P square will compensate. Okay. So this description is more complicated because you have to understand chiral bosons, but it makes the symmetry more manifest, right? Because the root lattice is the same. Now the 8 symmetry comes from the because you are choosing the 8 root lattice.
Hi.
Yes.
Yeah. So in the fermionic description, we had 8 sectors: NSR, NSR, NSR.
Yes. Here you have only 2 sectors.
Yeah. That's how we will describe in the chiral bosonic description that there
Because
are 2 sectors.
all the 4 sectors that came from the left sector, right, are all now part of this root lattice.
Okay. Thanks.
And one of the spinner, one of the 2 spinners. Because one spinner is projected out by GSO, right? So it contains the adjoint and one of the 2 spinners and their product. Yeah, GSO projects out the vector.
The other spinner will remain, and that would be the supersymmetric partner of this.
No, the supersymmetric partners always come from the right. Supersymmetric partners are these. Right? There is no story of GSO there. So there, the story of GSO gets replaced by what lattice you are choosing. Okay? Only for this lattice that you get modular invariance.
In the right sector, there still is GSO.
Right sector is identical, yeah. That is GSO.
There's some relation between the guys, IPs and IMs.
That relation is highly nonlinear. It's not a local relation.
But I can think of GSO projection as an action on eta s and IPs. Taking some of the eta
Yes.
minus eta.
Yeah.
That has no obvious.
No, that only relay, the only translation of that here is that here, for example, you have thrown away some points in the lattice.
Like some permutation between the
Well, I think see for E8 cross E8, for example, right? There is no analog of this. If you think in terms of SO16 times SO16 subgroup, right? Then the weight lattice of SO16 times SO16 contains more elements, right? Where it contains the SO16 vectors, for example, right? And the SO16, the other spinner that you have thrown out by GSO, right? So those will be there, and the GSO projection there is a reflection that if you think in terms of SO16 times SO16 lattice, weight lattice, you have thrown away some states. But once you are saying 8 cross 8, right? Then those states are never there.
There's no action of GSO on YMs.
On?
YMs.
No. No. So YMs are automatically, when you specify the root lattice, you have already implemented GSO. So all 4 sectors, right, are captured by just the root lattice.
There also, in a sense, like when we say E8 cross E8, after GSO only we got E8.
Yeah.
Here we are directly taking E8 cross 8.
Yeah, I'm just
Yeah.
trying to identify the middle step here.
Yeah. So middle step is if you start from the SO16 times SO16 root lattice, right? That has more vectors in the SO16 times SO16 root lattice. Right? More vectors.
Choices for P.
More choices of P.
Correspond to GSO odd state.
Yeah, which will correspond to GSO odd states as well.
And E8 cross E8 cross 8 root lattice only contains the adjoint. Because there are no spinners.
Yeah. Adjoint and its products. Yeah. Yeah.
At some we know that the left sectors and right sectors can be dealt independently, right?
Yes.
So can we perform the personalization on the right sector also and get rid of this NS and Ramon sector completely?
We can try it, right? I mean, for compact theories people have done, right? For non-compact part, it's not efficient because you want to maintain Lorentz invariance, right? No, it doesn't. This wall sheet supersymmetry that relates x mu, you don't want to mess, right? If you try to bosonize the psi mu's, then the Lorentz invariance will mess up, right? And typically, yeah, I mean, that's why you don't try to bosonize the non-compact part, right? But once you compactify, right, then the associated fermions, people can bosonize, and you can write things in terms of the bosonic theories.
What do you do with the ghost?
In fact, people do the other way. I mean, people have constructed theories where you fermionize the bosons, right? Compact bosons you can fermionize. So you can write everything in terms of the fermions. Ghosts are ghosts. I mean, you keep them.
You don't.
Beta gamma ghost you have not introduced. So once you introduce beta gamma ghost, you will see that you will bosonize them.
Those also you both.
But those are bosons, but you will bosonize them again.
They are bosons, na?
Yeah, beta gamma are bosons.
Not bosonization.
We'll do beta gamma next time. I mean, it's a whole complicated story. Okay. This week and next week, I think, because next week also there are talks. No, the person who sent it is not good. But anyway, this talk was good. So I'm glad that he didn't have it at 11:30. None of you attended? That's it. Anyway, these two people have to work on it. So you attended or not? Didn't attend?
Who said the name?
Don't